Neil. This really goes back to about 1974, when I became an academic after working in Plessy in the semiconductor industry and after doing my PhD at Liverpool in plasmas and fusion. I was looking for a research area to go into, and I came across mobile radio. There was a spectrum problem, there was certainly an oil problem, and it seemed to me a good idea to look at mobile communications and how we could use mobile communications to improve the overall situation. The only thing was, most people didn't support mobile communications, and indeed it wasn't a respectable research area. That's not a good thing for a young academic to do, but I've always enjoyed the challenge, and it sort of fits in with what we're talking about today. At the time of the start, as I was at Bath University at that particular moment in time, mobile networks were analog in nature, and of course the end of the 80s and the early 90s we started to see the introduction of digital networks, but the police networks were very analog, and they were waiting for their own digital system to come along. But the problem for the police was that not only did they suffer the normal problems of mobile communications, of multipath fading, which distorted speech, made it sound like Donald Duck, and made data transmission almost impossible, but they, such a highly distorted and very low data rates, they could be eavesdropped. And that wasn't a good situation. And I remember going to a meeting in Brussels where somebody said you couldn't get reasonable privacy on an analog network. Well, there's another challenge. So I got back to Bristol, and I remember saying, challenge here, we need to look at this. Can we come up with something that could make analog networks reasonably secure in the transition period from analog networks to digital networks? And fortunately, I'd got a research grant way back in '75 for looking at the science of radio wave propagation using these newfangled things called computers and minis and mini computers. And I got another grant in 1981 where, thanks to Frank Grimm, the then technical director of Pi, and Steve Barton, who was then, I think, at RAL, I had two grants which allowed work to really start on looking at the fundamental problems of mobile communications and so on. Anyway, the techniques developed then, those grants, by the way, the first grant was for just under £10,000, the second grant was around £60,000. Those two grants enabled an awful lot of fundamental work to be done. It informed us how we could reduce multipath distortion, remove it from the received signal to get high-quality data, and allow high data rate transmission and fading, and the first ever multi-level transmission of data and fading, and really allowed the whole idea of spectrum-efficient communications as we know it today to come about. So, out of that early work of '75, I was approached by the Group Managing Director of Securicore, Peter Toll, who wanted to buy a new radio system for his fleet of vehicles. And BT also at that time were looking, I didn't realize, but for executive cars and their own network. And I said, well, who's going to make it? Because he was quite keen to have somebody new into the field. And I'd had some contact through a BT contract with a Finnish company called Mobira Oy. And they provided me with an RF front end, the thing that selects the signal you want. And so I put them in touch with Peter Toll. And out of that, I designed the radio with colleagues, and Mobira Oy made it. And there's the radio you can see there. And I remember saying to them, so who owns you? And they said, well, we're part of a joint venture with a company called Nokia. And I said, well, what do Nokia do? They said, make paper, rubber products, and TVs. And this radio was very, very successful. And out of that, of course, came, I like to think, Nokia as it is today. The other interesting thing, I learned about finance. I got 2,000 quid for doing that. The photographer got 3.5. I then realized that engineers sell their technology too cheaply. Never again. Back to the Home Office and the police and their poor communication system. Well, the Home Office were bringing about a trial, which I picked up on, and it seemed too good to miss, and they wanted a scrambler, a speech scrambler that prevented eavesdropping, And if you had one of those old stereo systems, or radiogram, as used to call it in the old days, and you go towards the end of the dial, you pick up the police communications, and you could have all sorts of enjoyment. But that's wrong to do. I never did it, I know. But I heard about it. But the Scrambler had to deliver quality when the speech was unscrambled at the receiver. It also had to have a very small delay, because there's a big difference between go and don't go in an operation. So the first syllable had to be captured, and that was very difficult with the new digital systems that were coming along at that time. Low bandwidth expansion, low battery drain, all the usual sort of things, and obviously some degree of privacy and security, and that's a variable feast, and really to be reprogrammable and affordable. And so we developed a system which I persuaded GC Marconi, because I come from Merseyside, as you can tell from my dulcet tones originally. There was a company up there which made secure radio products called GC Marconi Secure Radio. So I rang them up and said, you haven't heard of me, I don't particularly know you, but I've got this fantastic idea. There's a Home Office trial. Are you prepared to come in? And we set about doing the Marconi Advanced Scrambler. And there were 5 options tendered from around the world. And the mass scrambler at Bristol was the only one selected for use by UK police forces. And I'm pleased to say it made quite a lot of money in the early times. Unfortunately, GC Marconi went under, but fortunately, that part was acquired by Motorola, so it's still being made today, and it's still being sold around the world. So I'm pretty chuffed with that. How did it work? Without going to the real nitty-gritty, it was really a frequency domain scrambler. And what made this possible? Well, way back in 1979, there was a fledgling company called Intel, which really came out of Fairchild, people like Noyce and Andrew Grove. And they came forward with the first digital signal processor, the 2920, the Intel 2920. And so if one looked at that, you could do a nice device that was really rapid and had good power requirements, by doing what was called frequency domain scrambling. So you take the speech spectrum, divide it up to 50 hertz chunks or 100 hertz slots, and you'd scramble that around, basically. You reorder it. And we did that with a whole pile of codes, and we had over 30 million codes to do it with, and then we had more codes for the keys that would allow the encryption process to take place. The main thing was, it was pretty good, I like to think. And if you go into YouTube, you can hear the scrambled and unscrambled versions, if you'd like to spend some time one evening doing that, or at lunchtime. And that was the system we made. It was handmade by us in the lab, because they needed some radios for the policeman's uniform, so we made one. And at the bottom of that picture there, you can see the unit. This is the Texas Instruments DSP. And it went into this unit here, and of course that was on the policeman's lapel. And the DSP process did all the sort of things you do in these sort of techniques: speech input, crypto engine, speech manipulation, speech output, speech synchronization. It's all got to be synchronized, and it's all got to be encrypted correctly. I think the interesting thing was, this is all about spectrum manipulation, and that goes back to the first grant from EPSRC, SRC as it was then, in 1975, which was further developed in 1981. And I remember looking at the spectrum manipulation technique. And if you look at it, I remember talking to David Dack, the deputy director at HP Labs, and he said to me, do you know, if you take your idea and you do this, this, and this. I said, I know, because Motorola are doing it in the States. They've taken what we've been proposing, and they're thinking of a similar thing. It's actually OFDM, offset frequency division multiplexing, which now underplays just about every communication modulation scheme in the world that's used at the moment. And interestingly, recently there was a big court case over patents, and I'm very pleased to say that the Bristol patent, the Bristol paper published in 1993 at Edinburgh, actually prevented the payments being billions, just hundreds of millions, as it turned out, for the industry. So, great impact from a very small beginning. The applications, well, MASC was first used by the Thames Valley Police before it was rolled out across all the UK police forces and other government agencies for that matter. Initially sold by GC Marconi Secure Systems. and now by Motorola. There's lots of anecdotal evidence. I remember hearing, I was talking to one police force, and they said, well, we've used it, and our level of crime's dropped around 10%. I said, so what's happened now? He said, it's 10% up all around us. So it was a great form of publicity for selling the Scrambler. So I was very delighted well, not delighted, it was great to see that people embraced the technique, let's put it that way. And, of course, the mass Scrambler eventually gave way to Tetra when the digital techniques came along, and sort of so on, which was only natural. But it is being sold around the world in lots of developing countries. And, but the spin-offs have been far greater. Say, there's the Motorola handset, the 6000E. Other related outcomes of the original SARC grant. And I'm saying that there have been great influences on other work that myself and my colleagues have played over the years, from those early days in Bath to what we've done at Bristol since 1985. Ray tracing for mobile radio networks, that was the original grant, looking at ray tracing. I remember the experts in propagation at the time coming to me saying, well, really, it's empirical, but if it keeps you happy messing around on a computer, well, academics have to do something, don't they? Thank you. Multi-level data communications and fading. We take it for granted now. The systems like Edge and wideband CDMA, 3G, 4G, multi-level, QAM-type systems, and so on. That's what we did. Lawish Hanzo was very kind to say and comment on the Bristol work about it being revolutionary. Hyperlan came out of a project called LoRa, and I remember hammering Hewlett-Packard at the time, talking to John Taylor and people like David Dack and Conlai Anson about why don't the States do something, because this was very European, what we were doing, which became Wi-Fi, and of course 802.11 came along, and also if you look at 802.11 you'll see many of the techniques have been developed at Bristol and by my colleagues at Surrey and at Bath and other places in those standards. So it's a great exemplar for the UK university system. Smart antennas. Today, we use smart antennas, MIMO antennas for improving network efficiency, data rates, and so on. They all came out of the linear ideas. You need to be able to steer beams. You need to be able to put amplitude and phase weights onto elements of antennas and drive them, so you need linear systems driving them. And incidentally, that technique was not accepted. I remember getting on my bended knee at Belfast Airport, because we'd been on an SRC visit to Queen's University of Belfast, saying, please give me half the money, and I'll just show the principle. And we got half the money, and we showed the principle. And we got the IEEE Transactions Prize for Best Paper. And of course, wideband CDMA that we did with Bradford University and Bell Labs in the States, Whippany, and also Malmesbury, and also with our colleagues elsewhere. So it was really a marvelous situation for us in terms of what was a very, very small beginning.